Good day, ladies and gentlemen. Today I'd like to go over page 83 in your packet, which was the quiz that was set up to review much of what we've done throughout this quadratics unit, this introduction to nonlinear relationships. Remember, most relationships in math, the entire universe of math outside of linears, are nonlinear. So this is the foundation of almost entirely what you will be doing for the rest of your mathematical career. I have to apologize because the quiz that I prepared for you actually isn't the one that was updated for last year. So there's some irregularities in it that aren't my preference, but we'll manage our way through it. Question number 1 on page 83, ladies and gentlemen, asks you to evaluate the given function, the useful equation, at the time -3, or 3 moments of time ago. In order to do that, my hope is that you recognize that this is a piecewise relationship, a function made up of two pieces. The first piece is quadratic and happened for all units of time less than 2 moments of time ago. The second piece is linear, and that's happening for all units of time from 2 moments of time ago into the future. So when you're asked to evaluate for 3 moments of time, my hope is that you would decide to use the quadratic relationship because that is the piece that is assigned or was observed as happening for all units of time 2 moments of time ago and prior to it. So in order to evaluate that, we would actually have to go to our function, and for 3 moments of time ago, substitute -3 using parentheses into the expression, and evaluate that on our calculator. So it's a good idea to reset your calculator, so I recommend that you do second, access to memory, plus sign, choice 7, scroll to all, hit enter, and scroll down and reset. On your home screen, if you clear out the text instrument information, you can begin typing. And you'd want to suggest that we have a half, which I always like to do as a grouped quantity. You could use your fraction key. And you'd substitute -3 using parentheses, be sure to square it, and subtract 5. If you were to do that, you'd find out that this relationship at 3 months time ago measured -1/2, choice A. You also could have gone to your function list and put in the exact expression with the variable. And in that space, you would see what this evaluates for every integer unit of time. And you could have simply scrolled back to 3 moments time ago. And you would have noticed that 3 moments time ago in your table of values, it measured -1/2. The result for choice 1 is, or the result for question 1 is choice A. The relationship measured -1/2 3 moments time ago. F of -3 equals -0.05, 0.5, -1/2. As I suggested, this isn't the quiz that I had updated for last year. And in the actual quiz that I prepared for last year, I had students evaluated 3 moments of time ago, 2 moments of time ago, and 8 moments of time ago. And the reason we did that was because that at 2 moments of time ago, students had to make a decision. That's on the boundary. Which expression should they use? And 2 moments of time ago, they should have used the linear expression because that is when the relationship is exactly or precisely equal to that boundary unit of time. And you would have to substitute -2 in place of x into the linear expression and evaluate appropriately. For time 8 in the actual quiz I would have liked you to have taken, you should have also used the linear expression because the linear expression is what we believe is going to be happening or has started happening 2 units time ago and will continue on into the future. So again, you would have substituted 8 in place of x in the linear expression to evaluate the relationship's value at time 8. Or if you had simply put that into your calculator's function list with the x variable, you could have gone to those units of time 2 moments of time ago and notice that it measured -3, and you could scroll to 8 units of time from now and see that the relationship would measure 27. That is evaluating a piecewise function from a piecewise function equation. Number 2 asks you to evaluate a piecewise function from a graph of a piecewise function. So technically, we could come up with the appropriate equation for this. Prior to 6 moments time ago, the relationship is linear increasing. We could figure out the rate of changes and the y-intercept if we just extended that towards the y-axis. From 6 moments of time ago to 3 moments of time from now, it's just doing the same thing. It's a constant function. Y simply equals 8. And from 4 moments time ago on, the relationship is decreasing linearly. And we can figure out what that is by determining the rate of change, the slope, as well as the y-intercept. But we actually don't need to see the equation because we could evaluate it just by observing the graphical features. We want to get really good at understanding that all of our observations mathematically could either happen from a graph, from an equation like we saw just a moment ago, or even in a table of values. So if we want to determine the value of the graph at 4 moments of time from now, we would simply need to go to 4 units of time from now on our graph. That happens to be a boundary. And on the boundary, we need to be certain that we're always going to select the closed circle as the prediction at that unit of time. So we notice that 4 moments of time from now, the graph measures approximately -4. I believe that circle should be down just a hair. So at 4 moments of time from now, the graph on the boundary is going to measure -4. Which of the values of g of x in the given piecewise function is true? And that should be choice B. 4 moments of time from now, the graph measures -4. And again, I apologize because this was set up as a quiz, and then I had it set up as a review sheet. And on the review sheet, I gave students an opportunity to make a bunch of other observations. I had them evaluate the relationship at time 0 right now, and at time 0, the relationship is behaving as that constant function. It's measuring 8. 7 moments of time from now, the relationship is in that decreasing linear segment. It's measuring approximately -5. 6 moments of time ago, we'd have to go back. That would bring us to the lower boundary. And on that lower boundary, once again, we would select the closed circle as our prediction, and that was 8. When we're asked when does g of x equal 0, we're looking for roots or x-intercepts. When does it measure nothing? And that happens one time way back here where it crosses the x-axis, and it appears to be approximately 8 units of time ago. When x equals -8, the relationship measures 0, or -8, 0. What is the value of the relationship at position A? Obviously, that is up on the constant function. It measures 8. And what is the value of the relationship at position B? That is in the decreasing linear segment, and that measures -7. So once again, I apologize for giving you the quiz when I should have given you the review sheet, because you could have done a lot more observations and really had your eye move around the graph and understand how to evaluate a piecewise function graphically. When you go on to number 3, these are some skills that some of the classes might not have had as much practice with as the others. So I'll go through them pretty quickly and know that we'll review them in class in addition to seeing them here. You're asked to investigate the patterns in the table of values by looking at their outputs, or their y values, f of x, and determining what type of mathematical relationship that would be. In the first table, you're supposed to notice that as time goes on, the measured amounts are decreasing by 3 over and over and over again. There's a constant rate of change, which simply means it's going down 3 and over 1, down 3 and over 1, down 3 and over 1. That's going to indicate a linear pattern. Linear patterns are just repeated addition patterns, and in this instance, that's what we're seeing happening throughout the table. When you look at graph table g of x, you're supposed to notice that the measured amounts are increasing by 9, then they go up by 3, then they decrease by 3, then they decrease by 9, and then they decrease by 15. There are 2 incredibly important observations you can make at this point. One is that there was a vertex, and because there's a vertex, a time and measured amount where there is repeat behaviors on both sides of that time, that's going to indicate that this is either an absolute value graph or a quadratic. So it's not going to be linear, that's for sure. Now, once we determine that, we need to decide if it's absolute value or quadratic. If the differences or the decreases and increases in the table are inverse non-constant amounts, they're opposites, but not the same opposite amounts, not the same number repeating over and over again, that's going to indicate that it's a quadratic relationship. There are other ways to determine that. We'll talk about it in class. When you look at the third table, h of x, we also notice that there's a vertex indicating seeing the repeated measured amounts on either side of it. So that means that we are not looking at a linear relationship, and therefore it must be either quadratic or absolute value. When we look at the rates of change, we see that throughout time, there's an increase of 1, and then 1 again, and then the relationship decreases by 1 over and over again. And because it is inverse or opposite rates, and they are identical, so it is constant rates that are exact opposites, that means that this behavior was going up linearly, up 1 over 1, up 1 over 1, then going down linearly. And because that's the case, we have an absolute value graph, which is kind of like a quadratic and a linear had a baby. I'm going to leave it at that, ladies and gentlemen, and we'll do the rest in class when we return. For question number 4, you ask which are true statements or observations about the given function. And this starts to really bring together the idea that we should be able to make observations and predictions and look at the information within relationships either as a graph, a table, or in an equation. So I hope when you look at this equation, there are several observations that you make. And the first being, hey, Chooch, here's what I see. There's a squared quantity, therefore it must be quadratic. In addition to that, it appears to be in vertex form. And in vertex form, the cool thing is I can see the vertex. The lead coefficient would be the amount being multiplied by the highest exponential term, which is the grouped quantity at this point. So the lead coefficient A is technically +1, which means this quadratic should be going up. The axis of symmetry is the time when the vertex occurs, and that's always in vertex form the opposite of the amount being added and subtracted to x. So the axis of symmetry is going to be happening 3 units of time from now. And the vertex must be happening 3 units of time from now when it actually measures 5, when you learn to read this relationship appropriately. When you go through and determine which of the observations are true, the first one suggests that the graph is a parabola, and that is 100% true. We know that quadratics make parabolic behaviors. That's the name we give for the shape of that U. It most certainly opens up or is concave up. That is true as well. The vertex happened 3 units of time ago to a measured amount of -5 is not true, because the vertex is happening in the future, not in the past, and that's an important observation to make. We need to know when that minimum value occurs or occurred, and in this case, it hasn't occurred yet, so that is false. The axis symmetry happens at time 3 is true. That is the correct observation. And the y-intercept value 0 we have to consider. We do not get to see the y-intercept in vertex form. The cool thing about vertex form is you can see the vertex, but you'd actually have to compute the y-intercept. The y-intercept would be a result of evaluating the function at time 0. So we'd have to substitute 0 in place of x. You could do that either on your home screen or in your table of values. So when you go to calculators, it's important to go to your function list, clear out what you have, substitute in the actual equation x less 3 squared plus 5, and go to time 0 in your table of values. And you'll notice that at time 0 it measures 14. That could have also been done on your home screen by simply substituting 0 in place of x. 0 less 3 squared, so it's going to be negative 3 squared, that'll be 9. And when you increase 9 by 5, you get 14. And that confirms our observation. The value of the relationship at time 0 was 14. So the y-intercept should be 14. It is not 5. That would have been false. And then you could indicate which of the responses represented all the true statements. Down below, once again, we're swinging back to a graph. So we're going back and forth between the graphs, the tables, the equations, and being able to make all kinds of observations computationally and mathematically throughout the different presentations. The first question is, what is the vertex? And my hope is that your eye immediately goes to the lowest point on this graph and notices that 2 units of time from now, the relationship measures -8. The equation for the axis of symmetry is simply the time when the vertex occurred, or it is also the imaginary vertical line that cuts the parabola perfectly in half, always going straight through the vertex. The vertical lines are always x equals equation. The equation for the axis of symmetry would be x equals 2. 2 units of time from now is when the vertex occurs. The roots are where it digs into the x-axis, or where the relationship measures 0, also known as the x-intercepts. And one of them happened 2 moments of time ago, and the other one is happening 6 moments of time from now. You could represent that as either -2, 0, and 6, 0, or you could simply say x equals, and fancy parentheses, those are set brackets, -2, 6. We don't need to know the y value because, by definition, the roots of 0 means that y would be 0. To determine the y-intercept of the value at time 0, you have to focus your attention on the y-axis. That would be right now. And right now, we notice that this relationship is measuring -6. Find out where the relationship crosses the y-axis, and it measures -6. The relationship evaluated at time 0 is -6, or we could say 0, -6. To determine the interval when the behavior is decreasing, our eye has to travel from left to right, from the past into the future. And as we first encounter the graph, even though there's an arrow tip pointing up, technically the measured amounts are decreasing as they approach the vertex. That would mean that all the times up to the vertex, the relationship is technically the measured amounts are going down and decreasing. So up to 2 moments of time from now, the relationship is decreasing for all values of x less than 2. The opposite would be true for when it's increasing. It's going to be increasing after 2 moments of time from now into the future. That's when the relationship is going to be going up for all values of x that are greater than 2. To determine when the relationship has negative measured amounts, that would be whenever we are in between the roots. Roots are when it equals 0, and in this case, it's below 0 in between those units of time. So that's from 2 moments of time ago up to 6 moments of time from now, and all values in between, we can expect the y values to be negative. The domain refers to how much of the x-axis are we using, and you could argue that we're simply going from 4 moments of time ago to, I believe that is 7 moments of time from now, but because there's arrow tips, it technically means there is an infinite domain. It means that if our graph were bigger, we would see this relationship further into the past and into the future. So our domain is technically infinite. It goes from negative infinity to positive infinity. The range, however, is a little more limited. The range, our measured amounts only went as low as -8, and they're going to go up to infinity. So we could simply say that all of our y values must be greater than or equal to -8 if we were to investigate a table of values. There's a lot of information in there, and I hope that it all makes a bunch of sense to you. If you get all of it, you're in fantastic shape. If you get most of it, you're in very good shape. And even if you get the majority, or at least the first observations, you are still in pretty good shape. Now, I have to apologize. You guys don't have a second page, so I'm going to need you to turn to the next page, page 84, the blank page. And there are still a few observations that I would like you guys to make. I forgot to print the page, but we can still do it together through the video and on the blank page. So on your blank page, ladies and gentlemen, question number 6 would like you to list the y-intercepts f of 0, or the initial values from least to greatest based on the relationships f of x, g of x, h of x, and p of x. And what's really cool about this particular question is that it's forcing you to transfer your information or your observations through the different presentations and with different mathematical relationships. So this is a really powerful question. For our first function, f of x, my hope is that you look at that and you're like, Tooch, that's totally linear. It's x to the first. And to determine the y-intercept, there are 2 things we could do. One is we could simply evaluate the relationship at time 0. And if we were to do that, we find out that it measures -5. Or you could have noticed that it is in slope-intercept form, y equals mx plus b. And you could have said, isn't the y-intercept just the b quantity? Shouldn't I know that at time 0 it's going to measure -5? And that would be really cool if you did. For the function g of x, in order to determine the y-intercept, you simply have to go to time 0 and make your observation. At time 0, g of x measures 4. Therefore, the y-intercept, g of 0, is 4. Once again, in h of x, you're given an equation, and this time you're given an equation that has x squared in it. This is quadratic, and technically it's in what we call standard form, descending exponential order. So our coefficients are a, b, and c. To determine the y-intercept, you'd have to evaluate the function at time 0. You'd have to do negative 0 squared plus 8 times 0 less 3. And there are two ways you could evaluate that. You could go to your calculator, and on your calculator, you could either, from your home screen, substitute in negative grouped quantity 0 squared plus 8 times 0 less 3, and hit enter. It measures negative 3. Or in your function list, you can simply substitute in the entire original expression, negative x squared plus 8x less 3. If you were to go to your table of values, you'd notice that at time 0, the relationship does in fact measure negative 3. Now, all of that is a lot of extra work, because technically you could have just said, Tooch, isn't it true that in a quadratic relationship in standard form descending exponential order, the y-intercept will always be the c coefficient, the constant numerical value on its own, because the x's will equal 0 and they'll all cancel out. And if you're able to make that observation, you could have done that question a lot easier. When you go to your graphical presentation, and in this case p of x, my hope is that you understand that's an absolute value graph. It's making a v. And that the y-intercept on a graph is always where the relationship intersects or crosses the y-axis. So that is where our eye should travel in making this observation. At time 0, we should notice that the relationship measures 8. So p of 0, the value at time 0 for function p, is 8. Based on those observations, you should be able to put the y-intercepts, the value at time 0, in order from least to greatest. We have f of 0 equaling negative 5. We have h of 0 equaling negative 3. Then we have g of 0, which equals 4. And finally, p of 0, which equals 8. And you can imagine all the different contextual real-life problems that would be incredibly important to observe or compute to determine what is the relationship measure now. Maybe right now we're trying to make an investment in a company that's making the most money, and we want to know how are they doing right now. Some companies would be in debt. They would owe money. They wouldn't be making any money at all. And some would be doing really well. And what an incredible observation that would be. Question number 7, I'm going to skip for now. It's an incredibly important question, and we really do have to come back to it. For the length of the video, I'll continue on. Question number 8 I do want to do, because in question number 8, it's showing up on Delta, and I notice that some students are struggling with it. You're asked to compute the axis of symmetry as well as the vertex for the given function p of x, and only an algebraic solution will receive full credit. So this is one of the skills that Delta is asking you to do as well. Now, what you should know about the axis of symmetry is that when we graph a quadratic, it's going to be either the minimum, or the vertex, I should say, is going to be either the minimum or the maximum amount. It's going to represent the turning point. So it is possible to go to your calculator and graph this relationship to determine the axis of symmetry. If you went to your function list, cleared out whatever you had, and substituted in positive 1/4 x squared less 6x plus 26, you could try and observe where the vertex occurs. In many instances, it will be difficult for you to do. We'll put it off of the graph because we want you to compute it algebraically. If you would increase your domain and range, you could possibly see this better. So it appears as though the vertex is happening further out into the future. I'll increase my domain up to 20 units of time from now. And it looks as though it's happening below my graph. So I'll make it go down 30 and see if that's far enough over and down to actually see the vertex. Well, there it is. It's happening a certain number of units time ago at a certain measured amount, beyond 10 units time from now. You could calculate it, but I'm going to save that for later on in the course. If we observe that table of values, we would know we have to go beyond 10 units of time from now, and we'd look for the symmetry or sameness in the table. And there it is. It appears as though 12 units of time from now, the relationship measures negative 10, and there's repeat or symmetry on both sides of the table. So by observing my table of values, I'm able to indicate where the vertex is and what it measures. That's not what the question asks you to do, and for Delta, that would certainly not earn you full credit. What we have to do is find that same information algebraically, because everything in this class should be able to be done, observed, or computed algebraically, or in a table of values, or on a graph. The algebraic opportunity to determine the axis of symmetry in the vertex comes from the axis of symmetry formula, x equals negative b over 2a. So it's important that you know that when we have a quadratic in standard form, the variables are a, b, c. I should say the coefficients are a, b, and c. A always belongs to the highest exponential term in any relationship, which in a quadratic is x squared. B would belong to the next highest exponential term, which in a quadratic is x to the fourth. And c belongs to the constant numerical value, or the least highest exponential term technically there's an x to the 0 here. A equals 1/4, B equals -6, and C equals 26. When we substitute that information into the axis symmetry formula, x equals the negative of b over 2a, we'd have to say that x equals the negative of -6 divided by twice 1/4. That can appear tricky to do, but it can all be done on your calculator. I'll begin to simplify that expression. In the numerator, the negative of -6 is just +6. And in the denominator, if you did twice times 1/4 on your calculator, you would get 2/4 or 1/2. To divide 6 by 2/4, you could use a calculator to get some help. Or you could simply know that you're actually multiplying by the reciprocal. So we have 6 divided by the quantity 2/4, also equal to 1/2. And we were able to determine that the vertex occurs 12 moments of time from now. X equals 12. When x is 12, we will see in this particular relationship, because a is positive and it's increasing over time, 12 units of time from now we'll be able to find the vertex. The question just becomes, what does the relationship measure at that time? And in order to determine that, we have to evaluate the function 12 units of time from now. P of 12 is going to be 1/4 of 12 squared less 6 times 12 plus 26. And that we would do in our calculated home screen. The relationship evaluated 12 units of time from now is going to be equal to 1/4 of 12 squared less 6 times 12 plus 26. And we're able to determine that this relationship 12 units of time from now is going to measure -10. And because the relationship measures -10, 12 units of time from now, we can say that 12 comma -10 is the value of the vertex. It's actually not that difficult to skill. And if I wasn't talking you through it, it wouldn't take very long at all. The additional actual questions on what I had hoped to have been the practice quiz for you folks, we do not have to do, but it is good to see what you would have been asked so you can recall all the different things you are supposed to be able to do from this unit. And the last considerations would have had you graph some of these relationships. So the very last question we won't do together, but know that one of the most important things that we spend a ton of time on is being able to graph absolute value graphs, or I should say non-linears, in addition to our linear observations from the beginning of the year. The last question is the system. It's more than one equation at a time. And the first relationship is an absolute value, which makes a V. And because it's nonlinear, it's typically graphed from a table of values. Absolute value graph is kind of like a quadratic, and a linear had a baby. So we like to get the ideal table to graph from, where our first y value is equal to our last. And a linear we graph traditionally without a calculator. We identify the y-intercept as well as the rate of change, and we graph appropriately. The solution to a system is where the functions intersect. In this instance, there could have been one solution, two solutions, or if the linear never hit the quadratic, there could have been no solutions. Ladies and gentlemen, this is the quiz that is reviewing much of what we've done throughout our non-linear introduction, our quadratic and absolute value unit. And I hope that a majority of what you've seen today makes sense. If it does, you're in really good shape. And if not, we'll continue to work on it. I will see you in class. Be well.